Hi all, in this video I am going to explain the classification of metals, semiconductors and non-metals on the basis of their conductivity and on the basis of their energy bands. On the basis of conductivity, let me see how we have classified metals, conductors and semiconductors. On the basis of the relative values of electrical conductivity denoted by sigma or resistivity rho that is equal to 1 by sigma, the solids are broadly classified as metals. They possess very low resistivity or high conductivity, where the value for resistivity is 10 power minus 2 up to 10 power minus 8 ohmic meter, and the value for conductivity is 10 power 2 up to 10 power 8 Siemens per meter. Coming to semiconductors, they have resistivity or conductivity intermediate to metals and insulators, where the rho value is 10 power minus 5 to 10 power 6 ohmic meter, and the conductivity sigma's values are between 10 power 5 to 10 power minus 6 Siemens per meter. Coming to insulators, they have high resistivity or low conductivity, where the resistivity values ranges between 10 power 11 to 10 power 19 ohmic meter, and the conductivity value ranges between 10 power minus 11 up to 10 power minus 19 Siemens per meter. The values of rho and conductivity given above are indicative of magnitude and could well go outside the ranges as well. Relative values of the resistivity are not the only criteria for distinguishing metals, insulators, and semiconductors from each other. There are some other differences which will become clear as we go along in this chapter. Our interest in this topic is the study of semiconductors, which could be elemental semiconductors, that is silicon and germanium, compound semiconductors, examples are inorganic if it is cadmium sulfate, gallium arsenide, CDSE, INP, etc. Organic, anthracene, doped thalocyanines, etc. Organic polymers, polypyrrole, polyaniline, polythiophene, etc. Most of the currently available semiconductor devices are based on elemental semiconductors, silicon or germanium, and compound or inorganic semiconductors. However, after 1990, a few semiconductor devices using organic semiconductors and semiconducting polymers have been developed, signaling the birth of a futuristic technology of polymer electronics and molecular electronics. We will restrict ourselves in this topic to the study of inorganic semiconductors, particularly elemental semiconductors, silicon and germanium. The general concepts introduced here for discussing the elemental semiconductors by and large apply to most of the compound semiconductors as well. On the basis of energy bands, how can we classify metals, conductors and semiconductors? Come, let's see. According to the Bohr atomic model, in an isolated atom, the energy of any one of its electrons is decided by the orbit in which it revolves. But when the atoms come together to form a solid, they are close to each other. So the outer orbits of electrons from neighboring atoms would come very close or could even overlap. This would make the nature of electron motion in a solid very different from that in an isolated atom. Inside the crystal, each electron has a unique position and no two electrons see exactly the same pattern of surrounding charges. Because of this, each electron will have a different energy level. These different energy levels with continuous energy variation form what are called energy bands. The energy band, which includes the energy levels of the valence electrons, is called the valence band. The energy band above the valence band is called the conduction band. With no external energy, all the valence electrons will reside in the valence band. If the lowest level in the conduction band happens to be lower than the highest level of the valence band, the electrons from the valence band can easily move into the conduction band. Normally, the conduction band is empty, but when it overlaps on the valence band, electrons can move freely to it.